Hello everyone, thank you all for coming. It's a real pleasure to be here. This is actually my first time in Frankfurt, and it's a very beautiful city, I must say. So yeah, thank you all for coming. Today I wanted to talk a little bit about the future of the way that we build applications, and particularly obviously around streaming, which is the technology that I work with mostly at Confluent. And this is kind of an interesting time, I think, because streaming kind of sits at this intersection between the way that we deal with data and the way that we deal with programs. And if you think about the way that we've done this traditionally, it's been pretty much the same way for a long time. Right? You write an application, and that application has all your business logic inside it. And you have some data, and you put that data in a database. And your application talks to the database, and the database replies with things that are useful for that application. So we separate these concerns. Streaming kind of gives us a slightly different lens on this, right? Because streaming is really about data that moves around, and maybe using programs like stream processors, which let us manipulate these things. So this lets us sort of think about the way that we write applications, but also the way that we deal with data in a slightly different way, and I think that's really interesting. So in this particular talk, I'm going to take kind of three different lenses on the future, and talk about how streaming kind of changes these things a little bit, and also touch on where I think these things are going to go in the sort of near future. So particularly, this idea of global applications. So many of you will have a global presence. You'll have different departments in different countries. Truly global applications are actually pretty hard to write, and we'll talk a little bit about that. We'll talk about how streaming actually allows us to build systems which are more self-service. So this is about the fact that the organizations that you work in are actually evolving all the time. And you're actually looking for that time to market, that ability to provision data very quickly and build new applications in shorter periods of time which are effectively self-sufficient. And then finally, we'll touch on this idea of serverless stream processing. So this is the relationship between serverless functions, if you've come across this idea of running functions in the cloud, and stream processing, which are, again, quite interesting, have a quite interesting relationship between one another. So just to set a bit of context, Kafka, which is the technology I work with, I used to develop this product some years ago. And Kafka is really a streaming platform. So most of you, if people heard of Kafka, I assume most people have heard of that. And out of interest, who's actually heard of Confluent, this company? We've got a few, okay, great. So most people will think of this technology as a messaging system. Right, so you can, if I have two programs, they can communicate with one another using this messaging system. One of them sends messages, and they send those messages normally on a topic which other people will find interesting. So if I have an application which creates something like payments, I might write these payments as they arrive or as they change out to a topic called payments, which other people can listen to. And that's that messaging system which sits in the middle of this picture. There's actually an ecosystem that sits around that, and that's called a streaming platform. And that has a number of actually pretty useful features. So at the bottom, there's a producer and a consumer. That's a very simple way for you to create messages or read messages from this messaging system. It also has these connectors. Right, so the connectors on each side. One lets you basically pull data from different data sources. Most of these will be databases, not all of them. If you do something like IoT, you might have an MQTT connector. You can pull data from Twitter and a bunch of other sources. But probably the most common use case is a database. It's like I have a database, I want to extract data from that database and turn it into an event stream, which I can then message to other parts of my system or other parts of my company. And likewise, on the other side, we have connectors which will push data into different types of database. Or potentially other things. So, for example, you can use a connector to invoke a Lambda function on AWS or one of the other cloud providers. And then finally, there's this notion of stream processing. And this is really where streaming differentiates somewhat. And there's a couple of different tools for doing this. So that rather small box at the top there, or there's two of them where it says SMT, that stands for a single message transform. That's actually part of the connector. And that's really just allowing you to do a transformation on an event. Right? So if I pull, let's say an order gets sucked out of a database, I might provide a transformation onto that to turn it into a format which I want other people to see. Or alternatively, on the other side, if I'm putting data into a database, I might take an event and one of these messages, and I might translate that into a format that maybe suits, I don't know, an Oracle database or a Cassandra database or wherever I'm landing this information. So that's a very simple transformation on an event. At the top is the stream processor. So Kafka Streams is one. There's also something called KSQL. This is similar to that idea of transformation, but it's a bit more complex. So it's actually allowing you to do operations not just on one event, but actually on many events. So either many events which arrive as a stream, or actually many different streams which come from different places. And we'll talk a little bit about that. So if you're familiar with the idea of traditional messaging systems, they've been around for pushing 30 years now. Things like TIBCO or ActiveMQ, RabbitMQ, IBM, Oracle all have products around this space too. A streaming platform or something like Apache Kafka differs in a number of significant ways. And the first one is probably scalability. So these kind of messaging systems can run at a pretty high scale. So you can get hundreds of machines in a single cluster. That's normally for a big data use case, like a big data streaming use case. So if you go to a company like Apple, who are basically ingesting, if you've got an iPhone, every time you open an application or close an application, all of this information is being pushed back through Kafka. And that kind of workload's pretty large, right? So that's actually about 100 terabytes a day of compressed data from the billion iPhones that sit around the world. So to do that, you obviously need a level of scalability. You can also store these data sets, and this is actually pretty important because when you're ingesting a large data set across this distributed messaging system, you actually need to be able to buffer that for some time, typically. Or often, as we'll see, store data sets indefinitely. And this becomes important when we look at stream processing. So there are topics out there with hundreds of terabytes in. You don't have to store hundreds of terabytes. Actually storing hundreds of terabytes and processing that data is pretty difficult, if I'm honest. It's like those really big clusters, they take a lot of operational management to deal with. But often we'll be working with smaller sets, maybe like 3 to 10 machines in a single cluster. And then finally, you have this idea of stream processing, which, as I said, is really about managing these large data sets. So if I go back to that Apple example of where you're ingesting data from people's iPhones, quite often, if you want to do any kind of analysis on that information, right? So that maybe you want to work out, maybe you're Apple and you want to work out, is the Facebook app behaving well, or is WhatsApp misbehaving? One way to do this is to sort of get all this data, you put it in a big Hadoop pipeline, and then you run a big query over it. And you can probably do that like every few hours. In fact, there was a time when it was basically a daily job. Stream processing lets you solve those kind of simple problems, working out, is an application crashing versus how many times is it being opened? I can sort of normalize these two things together to try and work out whether or not it's being unstable. We can use stream processors to do things like is to run queries like this, which will give us a real-time result. If you're familiar with databases, it's actually very similar to the concept of a materialized view. But hopefully that will come up later. So these things run at pretty high scale. Netflix, LinkedIn, both do more than 1 trillion messages a day. Twitter used this as the back end for, unsurprisingly, Twitter. And I said Apple use it. It's also used in a lot of normal institutions, banks, telcos, retail companies, etc. So to think a bit about actually how we start to program or build systems around streaming, we have to understand this concept of the event. And this turns out to be a pretty subtle and actually really interesting idea. it's taken me some time to actually really appreciate how the importance of the event. Because an event sounds like such a small and innocuous thing. You sort of think, well, what is an event? It's like something happened. A payment, somebody made a payment, somebody viewed a website, a program wrote a log line. These are all events. These are just all simple things that happen. But when we start to think about how events change our programming model, things become quite interesting. So firstly, events come in streams. So we have a sequence of events. We have creates a stream. And the order of that stream is very important. So a stream, one of the main primitives that a streaming platform provides is that it will ensure ordering of your events. But actually, typically based on some key. So you give it some ordering key. And then this stream processor takes this idea of a stream further by allowing you to do more complex operations. So we might have a stream of, let's say, orders and customers and payment and payment information. So if we had different systems around our organization or maybe different services around a microservice architecture, we can ingest, those might be creating events, just journaling the various things that they're doing. And we can combine those kind of data sets, those real-time data sets inside a stream processor, and we can summarize. We can join them together, much like we would join data in a database. In something like KSQL, we can actually then decide to omit any particular cadence and create some new streaming data set that we actually want to use. And this approach of using events and using streams actually changes the programming model quite significantly when we program with it. So in a sort of traditional approach, we tend to think in terms of kind of mutable state, databases, variables in programs, a singleton. These are all examples of basically mutable state, where we're always changing the value of some variable effectively. Also kind of RPCs, this idea of doing requests and responses. In the event-driven approach, we tend to think more in terms of events. Events are immutable, right? They never change. Right? Once an event is created, you never alter it. And then a stream is actually the thing that will represent how that, let's say, an order or a payment or whatever it might be, changes over time. And then we store those things in logs and we process them with stream processors. So to understand where this kind of fits from an architectural perspective, it's useful to think in terms of the way that architectures evolve over time. And most architectures should evolve, right? You should really start simple with the simplest thing that you can do, which is likely to be a monolith or maybe something distributed. So a simple application, which is an application plus a database. But then often you'll scale these things out. So for our monolith, we'll scale to being distributed. That gives us more compute power. We have more instances of our application, and they're all sharing data in a single database. If we move to something like microservices, we're actually making a slightly different trade-off. Right? So in a microservice application, each microservice has its own database. Right? So that gives it autonomy. So that each microservice can now change independently of the other ones because it owns its own data. And then if we move from that to something to event-driven, that's actually more about pulling in different use cases. So the important thing to notice about the microservice pattern here is that it's actually quite hard to communicate data between different microservices. And the reason this pattern works really well for sort of front-end applications. So if you're building a user interface, and you can have a bunch of different microservices. So you might have one that deals with your shopping cart, and one that deals with your product view, and another one which deals with maybe your payment interface. And the user interface is effectively joining these things together for you. But actually, if you want to do some more data processing work, let's say you want to do something like fraud detection, or maybe in a retail example, you want to manage a fulfillment process. You're going to need new services which need to be able to blend data from different microservices. So this is where the event-driven approach tends to fit in. So it's about decoupling from the front end. So we might plug in some new applications which are actually going to respond to events, and we're going to tailor those to these kind of offline use cases initially. Things like fraud detection or billing or fulfillment. Use cases that we just want to kind of plug in. And Kafka is sort of the entry point to this. So our services will have, let's say, REST interfaces or other RPC protocols, and they'll use Kafka to really broadcast their data sets to other interested parties, different systems that we want to plug in the back end. And the reason this is important is that as companies grow, and this is particularly true in enterprise companies, but it's actually true in all companies. It's as true in Netflix as it is in something like Deutsche Bank. As these companies grow, it's the back-end services that actually tend to grow faster. As a company becomes more complex, you actually have more of these offline processes. So you want an architecture where you can actually plug new things in. And this is what the event-driven approach gives you. And as this expands out, we can actually have multiple departments or even multiple regions connected together with the same set streams of events. So what's interesting about this from some slightly more futuristic perspective for me is this idea of becoming location independent. So if we have this event-driven model, the interesting thing about event-driven programs is because they're actually very loosely coupled from one another, they have this notion of location transparency. And what that really means is that I can write an event-driven program, and it doesn't really matter where it runs. It just needs to be able to subscribe to this set of events. So I can have a microservice application which is running in the US, and I can have other instances which are running, let's say, in South Africa and then some in Asia. And the same application can communicate via events, giving us this kind of global approach. And events also take us on journeys. So a common use case is to have something like a mainframe. Right? So it's pretty hard to innovate in mainframe environments. We often want to kind of unlock data from the mainframe so that we can do more interesting things. So a very common thing to do is to unlock information into a streaming platform from, let's say, a mainframe, a finance application that's running inside a mainframe, and then push that up to the cloud where we can do something like fraud detection. And then interestingly, because we're starting to build this data backbone, which is based on events, we can then extend that across different cloud providers or different geographies because of this location independence. So we might have certain services running on GCP and other services running on AWS, and we can actually move them around if we need to, assuming they're not making too much use of the proprietary components. So events let us run anywhere. We can run on a ship. Like a ship is actually a pretty disconnected environment. It's collected over a satellite network on cars, mobile phones, on a voyage to the cloud. Events give us this mechanism for moving in this direction. So the future here, from a streaming perspective, actually sits in having a single global abstraction. Today you can build global applications, and many people do. But I'm pretty sure that this ability to think about events in a global way will become easier to do and more powerful in these streaming technologies. So what that really means is, well, not only will we be able to have applications which run in different regions, but we'll also be able to manage failure, not just of maybe like an availability zone, but actually of whole regions. And this is leveraging this portability or this location transparency that comes with event-driven programs. So, for example, we might lose a data center and just fail over to one in a different part of the maybe the same geography or potentially even another one. So the second thing I wanted to talk about was this idea of self-service data. So notably that this event-driven model, and particularly the use of streaming platforms, allows us to base an architecture on a data set that's very truthful. That's to say, it's this raw data set which represents exactly what's happening in the world and makes our architectures a little bit more self-service. So systems that are built on events retain important information that would otherwise be lost. That's kind of a pretty core point about the event-driven model. Anyone heard of event sourcing? Is that a concept people have come across? Okay, so this is the base concept of event sourcing. So what does that mean? Well, imagine that you're creating a shopping cart. Okay, this is what a shopping cart's going to look like. Bob's got a pair of trousers, he's got a jumper, and he's got a hat. And we would almost certainly store that representation in the database exactly like that. If Bob decided to buy another pair of trousers, we just update the value in the database. It's pretty simple. Events don't do it like that. Events record exactly what the user did. And that's subtly different. Because actually what Bob did was he started off adding 2 pairs of trousers into his shopping cart. He then added a jumper. He then realized that he didn't really want 2 pairs of trousers because most people don't want 2 pairs of the same type of trousers. So he removed one of them, and then he added a hat, and then he added, what did I add next? No, I checked out. So the point is that this event-driven approach kind of keeps this user journey. It tells us what the user actually did. So it's non-lossy. And when we store data as streams, we retain this information. And there are other patterns for doing this, but the core pattern is that we're basically retaining exactly what the customer did. And then, so rather than having this lossy view where we just mutate state in a database, we keep all of this data as a set of events. And this is very truthful. It tells us what our application or our company or our user is doing. And then we can derive that stateful view from the event stream. We can always do that, right? We can always collapse back. Can't go the other way. There's no way to magically recreate the information that we've lost, but we can always use a stream processor to go back to that stateful view, which is the view that we would expect. So streaming is actually a form of event sourcing. This notion of basically keeping data as an event stream that exactly represents the outside world. So it's always non-lossy, and then we apply this projection to get us back to that kind of familiar view, which is the view that the user would actually see in their shopping cart. So events describe what happens, and it's actually the sequence of events in this model, the stream, which describes which describes how it happened, what the user actually did. So to take an example, or a few examples, in fact, if you think about something like a game of chess, the interesting part of a game of chess is not the fact that on the right hand, the end state was that we made it to checkmate. The interesting part of the game is probably, or at least as interesting, is how we actually play it. What are all of the different moves that get us there? Exactly the same thing is true for something like a stock price. Right? The closing price is interesting, but actually it's the evolution of that stock price over time which is potentially more interesting or as interesting. Exactly the same thing is true of a customer journey. As they wind their way through your application or potentially through a whole company. We want to capture all of this information about what they do, and so that we can provide insights on that. Formula One's another example. So in Formula One, we're optimizing to win, right? Everyone wants to win. But the actual process that a Formula One team go through is about capturing all this information and optimizing the driver and the car, both during that process and in fact afterwards. So you've got this this streaming platform running back at base, and that's basically doing all of this analysis. And this streaming platform turns those original 400 metrics into about 70,000 other measures. And this is doing a number of different things. So this is basically helping things like helping the driver them plot the racing line. So they're always trying to optimize what the racing line is going to be. It also helps them with things like measuring tire pressures and trying to work out whether or not, or how much the tires have eroded over time, so they can work out how many pit stops they need, and as well as doing things like aerodynamical modeling. So this is all done in real time. Obviously, it's a real-time use case. They need to provide feedback as quickly as possible to the driver. So the interesting thing about this is they use both physical models and machine learning models for these particular use cases. Machine learning is actually quite hard to do in motor racing because what happens is the cars actually change quite a lot, and machine learning models require you to have a data set that you can basically train them with, which only really works if you've got an accurate data set which represents your car, which you don't have. Although they do have ways of getting around this. So physics models are used a lot also. But one of the things you need to do in the racing use case is not only do you need to have real-time feedback, you also want to do things after the race. So after the race, you want to do things like, well, you want to work out, well, what happened at this particular point? Could we have done things differently? If the aerodynamics of the car was changed, would that have an effect? So one way to do this would be to build a separate system which does post-race analysis. And actually, they do some of that. But obviously, a more attractive thing to do is just to take exactly the same system which is running during the race. So we have all of these different machine learning models and these physics models, which we know are going to respond to real-time event streams. But we also have all of this data stored in Kafka, right? Because although this is a messaging system, it's actually storing all of our information for us. In their case, they're just holding all of the data that they get for a particular race. So if they want to either retrain one of the models or alternatively go back in time and work out what would happen if we change this particular engine setting or if we change this particular feature of the car's aerodynamics, they can basically rewind back in time and they just use the same stream processing algorithms that they were using originally to either try and work out why something happened or alternatively work out what would happen if they changed something. So with the data set stored in Kafka, you can actually do this simply using the same stream processing tools. So this is, again, another form of event sourcing. Right, so we're storing data inside the streaming system, and then we're rewinding back in time. This concept actually gets applied in a number of different use cases. So the New York Times is a completely different application of exactly the same pattern, right? So the New York Times is a pretty traditional website in many ways. And they actually store all their data in a thing that they call the monologue. So that first sort of rectangle where it says monologue, that's a Kafka topic. It contains all of the New York Times' articles right back to 1851. And that's actually everything. It's like images, articles, bylines, tags. Everything's just held separately. Right? So it's basically normalized in a database concept. And they use a stream processor basically to create views. So this is very similar to the concept of a materialized view, if you're familiar with that in a database, but subtly different, because the raw source of the data is this monologue. That then goes through a stream processor, creates a bunch of additional topics, which are just effectively denormalized events. So these denormalized events represent exactly what the view should look like on the website, and then those are landed in a set of Elasticsearch databases, which obviously then used by the front end to actually display information to the user. So this is kind of interesting because this is very different. This is like almost a different approach to this concept of schema migration. So in this instance, they don't do schema migration in a traditional sense. Actually, it's pretty hard to do in Elasticsearch anyway. So what they do when they want to change the view of the website is they basically just change the stream processor, which defines the view. They rewind back in time, just like we were doing in the racing use case, and then they replay that data, create a new view which matches the view of the website that they want. This is actually another example of event sourcing. So we can actually take these concepts and also apply them to larger architectures. So if we have, let's say we have a larger architecture which communicates through events. So this could be maybe, let's take a company use case or a large department. So we have a bunch of different event sources which are producing events because they may be interacting with users, et cetera, et cetera. We have a bunch of back-end systems, data warehouses, a variety of different applications, as well as event-driven applications, maybe doing like fraud detection or billing, et cetera. We can actually store some of these data sets inside the streaming platform. And actually, the way this tends to work in practice, so the New York Times use case is at the extreme end, right? They store everything in the messaging system. And you don't actually have to store everything. Quite a common thing to do is to store kind of core facts. If you're familiar with the concept of facts and dimensions, you store the facts for some period of time, and then you might store dimensional information, which is lookup information, customers, accounts, that sort of thing. You store those in their entirety. And this is actually really important because it gives you this concept of, it allows you to do enrichment using the stream processor. So let's take an example of what that might look like. So a number of different companies have something that looks like this. This isn't an off-the-shelf product, by the way. It's just in a variety of different companies. So actually Netflix have one of these. A number of banks have something like this. So the idea is that you basically just have a dashboard in the middle of the company. And the idea of this dashboard is that you can go to it and you can get basically any data set that you want. And you can get that data set materialized somewhere that you would like it. So if you like Oracle, you push it into Oracle. If you like Elasticsearch or Spark, you push it into one of those technologies. If you're just writing an application and you want to run you just want to write a microservice, then you take that approach, or maybe use a Lambda function. So you could log in, for example, and let's say I'm going to do something really simple. So I'm interested in orders, and I'm also interested in customers. So I click those two. And then next I'd define how much data I want. So in this case, I've got 1 week of orders. So I'm not going to take the whole data set. I'm not interested in that. But customers, I need to take the lot. And the reason is because for each customer, I'm actually going to want to enrich this information. For each order, I'm going to have to enrich this information with the relevant customer. And that means I need the whole data set inside the streaming platform. So then I apply a stream processor. And the stream processor is going to join these data sets together for me. So as events are created in real time, and actually the previous week, I will join the orders to the customers, and then I'm going to select out just the information that I'm interested in, much like as I would in a database. So in this case, I'm only interested in orders for the EU, and I'm only interested in Platinum clients. And then I'll push that information somewhere useful. So Spark, I might push it into Spark, so I can do some kind of data analysis. Or alternatively, I might choose to maybe push it into a microservice or a Lambda function. So the whole point of this is these type of architectures, particularly with these abilities to basically cache or store data sets inside the streaming platform, give me this very self-service approach to data. Right? If I want to write a new application, I can basically explore information in the company, and then I can suck it out and put it where I need it to be. So rich recordings, because the event-driven approach is actually recording everything, not just that latest version, of real-time use cases, as well as historical use cases, as we need, and all around this idea of making data self-service. So finally, I just wanted to talk a little bit about serverless, which is pretty interesting, I think. So the cloud really changes the game. Anyone do any serverless programming? Who's familiar with serverless functions? A few people. Okay, great. So serverless is actually really interesting. This is my prediction is this is going to be kind of big. So what is a serverless function? So very simply, it's just a function that you can write in some programming language. So Java, Node.js, Python, whatever you be. Just a function. You can write just like anything that you want it to do. Once you've written this function, you upload it to your cloud provider. So every cloud provider provides this service. And that cloud provider basically runs that function for you. And they run that function based on an event. So you write a function, so that maybe your function might just send an email, or maybe your function might turn an image into a thumbnail of that image, like compress it down. So you can do like a bunch of different things, complicated things or simple things, but it can't actually run for very long. You configure a trigger. So that might be an HTTP call. It might be an event created in a message queue. It could be a write to a database, very much like a streaming platform, or it could be something like a timer. And actually, so this whole idea originated from Amazon basically wanting to be able to do things off the back of writes to S3. So S3 is an object store. So if I write a big image to S3, I might just want to be able to spawn a function that just compresses it down into a nice little thumbnail, and I kind of don't want to have to manage like a big server to do that. I just want it to happen. I want the cloud providers to deal with this for me. So the reason these are interested is because they're completely hosted, right? And they actually provide this very nice auto-scaling property. So that function, when you upload it, it can only last for about 5 minutes. You only pay for the bit of time that you actually that you invoke it. But also quite interestingly, if you have, because these things are event-driven, and that's obviously everything that we've been talking about, if I have one event, if I write one image and I resize it, I'll just, obviously, that resize would occur and I get one function running. Let's say I actually write 1,000 of these objects. This object store, I get 1,000 events. Well, I would then actually get 1,000 parallel functions running at the same time. So this gives me this ability to do concurrency in quite an interesting way. And so the reason this is, so this is actually interesting for a number of different use cases. So you can think of it in terms of something like grid compute, but you can also think of it in something like maybe your build server or somewhere where, if you have a build server running, you're probably not going to run that on 1,000 machines, but you might run that on 1,000 functions. It sort of changes the way we think about these things. So Camille Fournier wrote, I wonder if serverless will become a thing like stored procedures, a good idea that quickly turns into massive technical debt. What she's really referring to is the idea that if we actually, because people actually build whole applications with these little functions, will this become like a complete nightmare? Because you're basically uploading all of this stuff into the cloud and you don't really know what's going on, and it's somewhat reminiscent of stored procedures. So what this really comes down to is the idea of whether or not you can really manage this kind of whether you can manage code in this kind of hosted environment. So for this to actually work, you need runtime diagnostics, you need monitoring, you need a nice fast deployment loop so you can actually get stuff done, you need to be able to do testing, you need to have an integration with your IDE that actually works and is really kind of efficient. And currently this is okay. It's not great, it's okay. But the reason I think this is really interesting, other than the fact that you get this beautiful concurrency, which comes with events, and I obviously think events are great, is that 3 of the biggest companies in the world, they really, 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 really want you to do this. And they're putting a lot of money behind it. So whilst it is undoubtedly harder to build an application in this way today, it may not be in the future. I think it probably won't. So basically, all of those things I talked about before, all those problems of can I actually tell what Amazon's doing with my function? What is my application actually doing? All of those problems are actually likely to be solved simply because the impetus which is behind this particular wave. So Sam Newman also mentioned, so Sam Newman's basically Mr. Microservices. He said, people who think serverless will solve all of their problems will end up sticking all of their data in one big database. Right, so if I've got these functions, I just have one big database at the end. That's basically an anti-pattern from a microservices perspective. You don't want to have one big database in the middle of your system or company. Certainly not if you're doing microservices. So the interesting point here is this. Whilst you might not put all of your data in a single database, you might put it in a streaming platform. And let me explain just briefly why. So these ideas of serverless functions are event-driven, but they're not streaming. And we've sort of covered enough to really understand that. So the interesting thing about a serverless function is it's just like a simple event-driven approach. So it can only respond to one event stream, right? So if I want to send an email and I need customer information, payment information, and order information, I'd have to have 3 separate functions. One, the customers and the payments are written to databases, and then when an order comes in, I'd have a function which would then read from the databases and put the data together with the order and send the email. So I have to kind of piece this whole thing together, and this is actually a little bit inefficient. The streaming approach is slightly different. In the streaming approach, the stream processor combines all this information together. And basically what this really means is that this can operate at maybe something around 100,000 messages per second per thread, whereas this example would go maybe like 10 or 20. Strictly, actually, that's a slight lie because the email bit would not work that fast. But as we'll see, that doesn't really matter. So what's really interesting about this is that you can take something like a stream processor, which is able to do all these join these various different event streams together, and create this enriched output, and push that into FAS, these serverless functions. So this basically turns So this creates something which is actually very similar to the way we would traditionally write a program. So if you think if you look at the way that that KSQL node, this stream processor, is actually stateful, much in the same way as a database is stateful. So we're starting to split our application, just like in the way that we would split an application into database and application layer. In an event-driven world, we're starting to split our application between simple functions, which perform business logic, and operations that we want to do on events, which will actually be stateful. So for example, that join, that KSQL node has to be stateful. Actually, it's the customers, because it has to enrich against a set of customers. It has to be state held inside the stream process to do that. So in the future, I think we'll actually also see these functions if we use these stream processes as a data layer for serverless functions. We can start to see them inherit some of the richer guarantees. But the thing I think is particularly interesting is that if we think about this traditional approach where we have applications and a database, and then we have this event-driven approach where we're basically pulling data together from a single FAS or a single application. Those are kind of the traditional approaches. The streaming model gives us this thing that's a bit like a database, but very much designed for this event-driven world. So on the far side, we're separating our state into a stream processor and our business logic into either an application layer or in this case, a serverless function. It's very similar to the way in a traditional world we split our stateless application into our application tier and our data tier into a database. So, in summary, events give us location transparency. That gives us a really good mechanism for building global applications. It also gives us, because we can store data sets in the event stream, that gives us this approach to make data very self-service, to push data where we need it, and actually create systems which can make data available in a sort of self-service manner, based on this raw this concept of truthful events. And then finally, we can take this concept of being able to store data in the streaming platform to create a kind of data layer, which has some parallels with traditional databases, but it's very much oriented around this event-driven world. And that's pretty interesting when we start to look at event-driven architectures and on the cloud, serverless architectures using serverless functions. So you put it all together and you get this kind of these global systems with stored events and cloud-native stream processing. And that's all I had to say. Thank you very much. Sorry if I went slightly over time. I've gone a few minutes over time there. So my name is Ben Stopford. I work at Confluent. There is a book which talks about some of these ideas. If any of these ideas were interesting or intriguing, there's a book that talks about a lot of the concepts of building event-driven systems. We're giving a few of these away at 11 o'clock, so that's in 12 minutes. So if you'd like one, it is in English. I don't have a German copy, unfortunately. But if you'd like one, please come over. And if anyone has any questions, I'd be happy to ask them here or over at the Confluent booth afterwards. And questions are always really welcome. So yeah, do come over and say hi. Thank you very much for taking the time.